In this video, we're going to start the process of trying to find suitable models from sets of data. Generally speaking, real-life bivariate data does not follow mathematical rules exactly. There'll be some degree of error in the figures that we observe. So if we're attempting to create a mathematical model for real-life data, it's important to start with a reasonable amount of data and then to use all the data to create the model. A reasonable model can then be used safely to make predictions about new data values that lie within the range of values considered. Using the model for data values which lie well outside the range of values of the data should be treated with the utmost suspicion. Given a set of bivariate data, it's worth starting by obtaining a scatter diagram and looking to see whether the data seems to be a linear rule, that is a rule of the form y equals mx plus c, or an exponential growth or decay rule, or a power law. So it's important that we should recognize each of these different types of graph. Now, a straight line graph is fairly obvious. In the previous videos, we've looked at exponential growth and decay rules. So, an exponential growth curve looks something like this. It's growing rapidly. It's got a formula of the form y equals a e to the kx, where k is positive. Or we could write the formula in the form y equals a b to the power x, where b is greater than 1. An exponential decay curve has a similar formula to the previous one, but clearly decays rather than grows, and it's got formulae y equals a e to the minus kx, where k is positive, or y equals a b to the power x, where b lies between 0 and 1. So those are the typical exponential growth and exponential decay curves. The power laws are if we've got a curve of the form y equals kx to the n, where k is positive and n is bigger than 1, that grows quickly from the origin. If we've got a power law of the form y equals kx to the n, where k is positive and n lies between 0 and 1, then it passes through the origin and grows, but nowhere near as quickly as if n was bigger than 1. And if we have a power law with a negative value of n, then the line x equals 0 is going to be an asymptote to our curve, and also the line y equals 0 is going to be an asymptote to our curve. So in other words, as x tends to 0, y is going to tend to infinity, and as x tends to infinity, y tends to 0. The data we've got here shows the population of the UK recorded in the UK census, which were taken in the years 1801, 1811, all the way through to 1901. For what follows, we're going to regard 1801 as being t equals 0, and 1901 will therefore be t equals 100. So t is the number of years after 1801. We're going to try and produce a mathematical model for the growth of the UK population during the 19th century. So the first thing to do is to produce a scatter diagram of the data. And the scatter diagram for this data looks like this. And you can see that it is certainly growing more quickly towards the end than it was at the beginning. So that suggests that we might have an exponential growth model for this data. If we've got exponential growth, then the relationship we'll have is if p is the population t years after 1801, we've got a relationship of the form p equals a e to the kt. Now, having the both a and the k as unknowns tied together in a single term is not dreadfully convenient, and it's very difficult to find the value of a and the value of k from the scatter diagram that we had on the previous page. However, if we make use of logarithms, we can get a much better format for the equation, which will help us greatly. So, taking natural logarithms of each side, we've got the natural logarithm of p is the natural logarithm of a e to the kt. Now if we go back to our laws of logarithms, the natural logarithm of a times e to the kt is going to be the same thing as the natural logarithm of a plus the natural logarithm of e to the kt. That was using rule 2. Using rule 4, the natural logarithm of e to the kt is going to be the same thing as kt times by the natural logarithm of e. So we've now got the natural logarithm of p equals the natural logarithm of a plus kt times by the natural logarithm of e. But the natural logarithm of e is log to base e of e, and log to base e of e is equal to 1 simply because e is the same thing as e to the power 1. So we're using our first rule of logarithms. So we've got the natural logarithm of p equals the natural logarithm of a plus k times t. Now for a moment or two, let's put q equal to the natural logarithm of p, and let's have c equals to the natural logarithm of a, in which case our equation natural logarithm of p equals natural logarithm of a plus k times t becomes q equals kt plus c. And that, of course, is the equation of a line of gradient k and with q-intercept c, where c is the natural logarithm of a. So we have shown that if the model p equals ae to the kt is appropriate, then a graph of q, which equals the logarithm of p, against t will be a straight line of gradient k and with q-intercept equal to the natural logarithm of a. So there's the important result that we've just commented on. So what we're going to do now is we're going to take our table of results and add the values of q. So q is simply the natural logarithm of the p-value. It's the natural logarithm of the population. And now we're going to have a look at the scatter diagram of q against t. And if the model p equals ae to the kt is appropriate, then the scatter diagram should be suggesting the graph of q against t is a straight line. And there is the scatter diagram for q against t, and we can see that it is very close to being a straight line. We could add a best fit line to this data either by eye, or we could use our calculator or computer to find the regression line for q and t. There's my best fit line added to the scatter diagram. We said the gradient of this line would represent the value of k. If I take the point on the regression line where t equals 100, I can see the q value is 17.26. If I take the point where t equals 0, the q value is 15.87. So I can use that to calculate the gradient of my best fit line. So the gradient is the q step divided by the t-step. So that's 17.26 take away 15.87 divided by 100, which gives me 0.0139. The q-intercept is the value of the natural logarithm of a. Now the q-intercept is 15.87. So I've got 15.87 is the natural logarithm of a. So a must be e to the power of 15.87, which is 7,803,000. So putting everything together, we have now got that an appropriate model for the population P of the UK T years after 1801 is P equals 7,803,000 times by e to the 0.0139 t. So let's have a look at the original scatter graph that we had with the model P equals 7,803,000 e to the 0.139 t added to the scatter diagram. And we can see that the scatter diagram and the curve are in good agreement. So we could perhaps use this rule to make some deductions. So for example, if we wanted to estimate the population of what the population of the UK was in 1827, well, 1827 is 26 years after 1801, so we need to have t equals 26. So when t equals 26, we've got P is 7,803,000 times by e to the 0.0139 times 26. And that comes out to be somewhere around about 11,200,000. If we want to estimate the rate of change of the population in the year 1858, well, 1858 is 57 years after 1801, so we want the rate of change of the population when t equals 57. Rate of change is the gradient, so we need to do some differentiation. We've got dp by dt, then is going to be 7,803,000 times by 0.0139 times by e to the 0.0139 t, which simplifies to dp by dt is 108,500 times by e to the 0.0139 t. And if I now substitute t equals 57 into that, I obtain dp by dt as 240,000. So during 1858, the population was increasing at a rate of approximately 240,000 people per year. Now on the final diagram, I've continued the data and the scatter diagram into the 20th century. So here's the data for the 20th century. There's the scatter diagram for the 20th century. And you can see that once you start moving into the 20th century, the curve ceases to give us a good model for a population growth. That's probably due to the effect of the First World War and also the recession and slumps there were during the 1920s and the 1930s. But certainly it gives us a very good illustration of why it is not a good idea to use models to make predictions about values lying outside the original data range. That finishes our first look at finding suitable models from data. In the next video, we'll be looking at how to find suitable models from data where a exponential growth or exponential decay is not appropriate.